Thank you. So I'm the Mattias, and I'm the technical lead for the TEMU simulator, emulator. So TEMU 2 was released a couple of years ago, in 2015, and the latest release was this summer, was version 2.3.5. And TEMU 2 supports the simulation of instruction level simulation of ARM, PowerPC, and Spark V8 targets. Supports multi-core simulation using a single thread with round-robin scheduling between the processor cores. And we have 4 different Leon configurations, from the ERC32 to the Leon 4. We have APIs for bus modeling, like SpaceWire and CAN and so on. Lots of models of various GR-lib peripherals. And we have a memory simulation system which supports single event upset and multiple event upset injections. And TEMU is fully deterministic, meaning that down to the instruction level, we can always repeat the execution stream exactly. It's used with different customers and also internally in Terma. We have one customer using this for a real-time GR740 RC simulator. We had some people, we developed a Star-Dundee adapter for TEMU's SpaceWire models, which lets you connect directly to them and send SpaceWire packets to real hardware. That can be delivered. It's not part of TEMU, but we have it available. We know a customer also did a bridge from our CAN bus model to their own USB CAN brick and talk to real hardware, but that's all I know. That's what they told me. We use it in software validation facilities, flight software development internally, and it's been used in the STEC Eagle Eye software validation facility. So, TEMU 3 then. This was just released pretty much 1 month ago. And there's some fairly major improvements. One is there's a new command line interpreter. The previous one was line-based and not particularly advanced. It was made for interactive use only. The new one is a recursive descent-based parser. It's backwards compatible with the old one, but we have if statements with curly braces and blocks and stuff like that. The performance of this has been greatly improved. We have added firstly we rewrote the interpreter engine to use a new model which is much faster. Then we have added the binary translator for the Spark target at the moment, not the other ones, but it's coming there as well, I guess. And with the release now, we are capable of emulating a single GR740 Leon 4 core in real time. So, but the Leon 4, the GR740 has 4 cores. So what do we do about that? And I'll come into that soon. We added several models and bus models, PCIe, GR-IO MMU model, IRQ AMP, and so on. And we also have an SMP2 runtime library or plugin in TEMU, so you can actually take SMP models and schedule them inside TEMU instead of scheduling TEMU inside an SMP model, sort of turning it upside down with respect to the simulator. But it's more natural when you're debugging software. So TEMU 4, which is not released, is under development. And what we're adding here, primarily for the performance side, is a parallel multi-core scheduler. We have a prototype that exists, and it started passing tests as of Friday last week, so yay for that. If you have enough host cores, you should be able to run GR740 in real time, simulated on this. We're looking at adding more models always. We have a System C runtime library that we sort of bridging between TEMU and System C that we're interested in putting in as a default thing here. We also especially want to focus on improving the software debugging and so on. So a bit about the performance. We ran some micro benchmarks on various things. So typically, integer workloads, we get 250, 300 MIPS. That's millions of emulated instructions per second. It's not dry stone MIPS, which is an artificial measure, but this is simulated instructions, so that's basically a bit faster than a 250 megahertz processor because they don't do one instruction per cycle. If you just have add instructions, okay, you get like 2.4 GIPS, but it's not very realistic, but it's nice to look at least. This was on a sort of 2019 laptop that we ran this. For the parallel builds of TEMU 4, we have produced this nice graph. I'm not sure why I did a line chart because it absolutely makes no sense in this. You have 2.5 processors or something like that. This is 4 simulated cores for the GR740. Some codes, some of the cores, these are running a certain percent of the code in idle and doing some work a certain percentage. So these are normalized numbers, but basically at the lowest bottom black line, you see the theoretical maximum basically from assuming there's no synchronization overhead between the cores, and that's just maths. So it's fairly good, the speed up we get here. And this is running on, that's for 2 threads. We're quite happy with this, actually. So we have run it on 4 threads as well, but it was a bit hard to get access to a machine with enough processor cores. And we had a lot of issues trying to produce this because IT gave us a Docker machine running inside a VM, running shared with other people, and we saw that we didn't get any speed up because, of course, we had 2 virtual processors that was just running sequentially. But this is now what we get when we put it on real hardware. So that's so a bit about the virtual platform supported by TEMU. So we have the processor models, but we also have all the peripherals. And we have a model of the ERC32, including the MEC memory controller. I'm not sure if anyone wants to use this anymore, but it's there. We have a model of the AT697F with a Leon 2 core, various Leon 3 based systems, UT699-700, and the dual core GR740. These are just config files, actually. You can assemble your own virtual platform if you want to. And of course, we have the quad-core Leon GR740. So this simulates the complete systems, including GPIOs, Ethernet, 1553, SpaceWire, CAN, and so on. The APIs for writing bus models is fairly straightforward, and there are tutorials for it. You're encouraged to adapt these. So for example, you want to change the amount of RAM for your GR740, go ahead, you just change it in the config file. You want to add an extra UART because you want to, you can do that and map it into memory wherever you want. And change the clock frequency to 2 gigahertz, go ahead and see if the operating system survives that. So, so what's in this? Well, on the bus modeling side, we have AMBA, CAN, Ethernet, 1553, PCIe, serial signal, or GPIOs basically, SpaceWire, and SPI. We have on our website, we have a list of features which should be up to date, but this was updated on this slide day before yesterday, I think, so it's up to date. And on the right-hand side there, you see all the GR-lib models that we have modeled. We typically add them when people need them. So I think they cover most of the GR740. Maybe there's one missing or something like that, but it's stuff we add when we need. So how do you use TEMU? Well, one way you can use it is for software debugging using the command line interface. Well, you can actually start up the GDB server if you want to. But each, in that case, you get one core is mapped to one thread in GDB. So it is non-intrusive, so it doesn't modify the state when you run GDB that way. But it's maybe, it doesn't represent one thread is one thread on the software running is not one thread on GDB in that case. We have a built-in assembler level debugger. We also have built-in dwarf and source level debugging. It's a bit basic at the moment, but it works for what we're doing with it. You can load multiple contexts for this at the same time. So you can debug the boot software and then step into the application software from it. And you can have both source level debugging contexts loaded at the same time. So we try to keep this, we want to focus a bit on the programmer productivity here and when you're debugging interactively. We're happy to add features for others. So to the right, you see like how to instantiate GR740. We just run the GR740 script. Then we say, okay, let's load into the memory from this a file. And then remap paths is a feature, so we can basically say that the certain prefix are remapped internally if you're looking at source code, because you took your flight software image from your CI/CD system, but you installed it in your home directory somewhere. So then we need, how do we find the source code there? So that's possible. And then you can just set the breakpoints in the specific context. How do we control TEMU except from the command line interface? Well, we have a C API actually, which is there for embedding TEMU and for writing models. And as I mentioned, we have the GDB remote serial protocol. So TEMU was built from the ground up to be embedded and to be driven interactively with the command line. So the command line is just using the APIs that we have publicly exposed. So people are embedding this in software validation facilities, like running in SimSat or Eurosim and so on. But we can also just run TEMU if we want to. I/O models, well, you implement a certain memory transaction interface for implementing when you're doing this. You can implement the model directly as a TEMU model if you want to, or you can forward the calls to an existing models like an SMP model, similar. You have to have this model with a transaction interface from TEMU because we need to map it into the TEMU memory address spaces. So we have that as a requirement. So we have some work to do in the future, just to finalize this. One is we're, of course, looking at the GR765 and RISC-V, and we're open for, and also we want to improve the software debugging capabilities to make it a sort of a prime target, that you want to use this instead of GDB or Eclipse or something like that. So I think that's it. Any questions?